Swayam Prabha. Digital India. Educated India.
Okay, so in this lecture, I'll be talking about certain aspects of absorption. So first, we'll talk about how do we obtain this equilibrium curve, which is very important to do mass transfer calculation for an absorber or stripper. Secondly, we will do material balance. So we have done material balance for a generic two-phase system, but now we will apply this material balance for a gas liquid operation in the context of absorber and stripper. And thirdly, we will specifically discuss about something called minimum liquid circulation rate. And finally, we will do an example problem. Now, the equilibrium curve is something that relates the equilibrium solubility of a solute in a liquid. Okay, in the chemical engineering thermodynamics course, you must have studied something called solubility of gases in a liquid. Okay, so here we are talking about something same. If I have a gas mixture and one of the solute is soluble in a liquid, how do we estimate the solubility? And that solubility is what we call as a equilibrium curve in the context of absorption. Okay, so the solubility curve is actually plotted here. On the y-axis, the partial pressure of the solute in the gas phase is marked. On the x-axis, the mole fraction of the same solute but in the liquid phase is marked. Okay, so this is what we have been looking at as y versus x as an equilibrium curve in the previous classes. And what is shown in this particular plot is a realistic solubility data for set of compounds. For example, data is given for HCl at 10 degrees Celsius, ammonia at 10 degrees Celsius, ammonia at 30 degrees Celsius, and sulfur dioxide SO2 at 10 degrees Celsius. First of all, if you look at the data corresponding to same temperature, let's say 10 degrees, between HCl, ammonia and sulfur dioxide, by looking at the shape of these curves, you can tell which gases are more soluble and which are not so soluble. So here the liquid is water. So these solubility curves are specific to a given solvent. Okay, so here we are talking about solubility of various gases in water. You can see this HCl has the smallest slope, meaning this HCl is actually very soluble gas. You may recall in one of the previous classes I talked about the equilibrium curves with a different slope. When the slope is very small, we associate them that as a very soluble gas. When the slope is very high, it is sparingly soluble. In that context, SO2 will be very sparingly soluble. So why do we say this is very sparingly soluble? Is because if you look at this curve, it has a very high slope, meaning if I have to have a small change in the X composition, that is, if I have to change the composition of this gas in the liquid, I have to increase the partial pressure to a greater extent. Okay. Whereas if you look at this HCl, you can see that a small change in partial pressure results in a very large change in the liquid phase composition, and this we associate as a very soluble gas. So that's a differentiation between these two kinds. Ammonia lies something in between. Okay, it is moderately soluble gas in water. So clearly the solubility data depends on the solute in question as well as the liquid that we are talking about. another data we can infer from this plot is if you take the same component like ammonia, but look at the data for two different temperature at 10 degrees Celsius versus 30 degrees Celsius, you see that as you increase the temperature, the solubility decreases for the gas in the liquid. Okay. So, the solubility data, which is essentially what we call as equilibrium curve, so it depends on the solute chemistry, the molecular makeup of the solute, it depends on the solvent or liquid properties or chemistry, and it also depends on temperature. So, this is very important because sometimes equilibrium may be limiting the mass transfer operation, and we can change the temperature so that we can even manipulate the equilibrium curve itself. Okay. This is something you must have studied in chemical reaction engineering also, where when you have a reversible reaction and you want to have a very high equilibrium constant so that you can move the equilibrium towards more of the product side, and you can do that by looking at pressure temperature dependence of the equilibrium constant, so that the reaction can be shifted more towards the product side. Similarly here, the temperature can be chosen such a way that whether you want to make the solubility more or less. Okay. So, when do we want the solubility to be more and when do we want the solubility to be less? For example, if you are looking at absorption as a problem, that is a solute will have to be removed from a gas to a liquid. So, here you want to operate at low temperature as possible, okay, because at low temperature the solubility is more. Now, let us say you have got a liquid, after the operation is done, the liquid comes out with a solute in it. Now, let us say you want to recycle this solute so that you can recirculate and reuse it. So, now you have to remove the solute from the liquid. So, now you have to play with the solubility. The way you do it is you increase the temperature in a stripper where the solubility will be decreased. Now, the solute will be removed from the liquid to some another gas, another carrier gas. So, by looking at absorption and stripping, it is mainly done by the same solute solvent system, but operating at different temperatures. So, that is why studying the equilibrium data or the solubility data of a gas in a liquid is very, very important, and this is something you must have done in chemical engineering thermodynamics in about how to calculate these equilibrium curves. Now, despite that, you can use the VLE calculation methods to calculate the solubility, but there are some very simple models we can use for solubility predictions. One such is Raoult's law. So, Raoult's law is applicable for a gas liquid system, equilibrium system, where we say the partial pressure of the solute in the gas phase is equal to the vapor pressure of the same solute at a given temperature T times the mole fraction of the solute in the liquid phase. Okay, this is Raoult's law. So, this is partial pressure of solute in the gas, and this is the vapor pressure. Vapor pressure data is available as a function of temperature using Ontine equation or many other models, and X here is the mole fraction of the solute in the liquid phase. Now, if you take this equation and divide by the total pressure of the system, then you get in terms of mole fraction in the gas phase, Y star is equal to PV by PT times X. You can see that the temperature dependence comes through this vapor pressure, and the vapor pressure data is specific for a particular solute. And this is usually used if the gas phase and the liquid phase are ideal. Both phases are ideal. This is probably the most simplest equilibrium curve you can think of, okay, where both the gas as well as liquid are considered to be ideal systems. Okay, the gas mixture is ideal and the liquid mixture is also ideal system. But this applicability of Raoult's law is very much limited to very few systems because of the nature of this assumption that both gas and liquids are to be ideal. Many times maybe the gas is ideal but the liquid is not so ideal. Okay, so then this law is violated. So inspired from the form of this Raoult's law that says y is proportional to x, another law is very famously known is this Henry's law, defined as y star is equal to some mx. Okay, sometimes we write this as hx, where this is the Henry's constant. And this will be also function of temperature. This constant will be a function of temperature. And this data is something that is available in the tabulated forms. If you look at Perry's handbook, you will see list of Henry's constant for various solutes in various liquid systems. Now, if you go back to this solubility data I showed, the curve shown here as D, this is basically the Raoult's law's prediction. For ammonia at 10 degrees Celsius. So ammonia's data is somewhere here, and the Raoult's law, if you apply, that will follow this line D, okay, which is, let me finish. So Raoult's law clearly is inaccurate in explaining, let's say, ammonia's solubility data, right? On the other hand, if you apply Henry's law for this problem, that is line E, and you can see that this fairly works for low mole fractions. So if the mole fractions of the solute involved in the gases and liquids are very small, Henry's law is a good approximation. Okay, Raoult's law is not so much accurate. Okay, that's a takeaway. But if you go to larger and larger mole fractions, even Henry's law is violated. Then you have to look at the actual details of the, it may become non-linear, okay, and you have to take the proper functional form like this. So let me write, this is Henry's law. So Henry's law is applicable when mole fractions are low. Or in other words, for dilute conditions. For all ranges of mole fractions and accurate equilibrium solubility data, so you have to either refer to experimental data or perform VLE calculations using non-ideal gas mixture and non-ideal liquid mixture models. So this involves fugacity and fugacity coefficients, and this involves activity and activity coefficients. Okay, so you can do a full scale VLE calculation over a range of mole fractions of your interest. Okay, so when it comes to, so in subsequently, when I look at when I think about equilibrium curve, you have to immediately relate that these data are obtained either from Raoult's law or Henry's law or a proper VLE calculation or experimental data. Okay, so we will not discuss further about how to obtain the equilibrium data. Okay, this is where the equilibrium data is obtained, and we will consider this is something now available for us for further calculations. So next we will move on to material balance. So this is my absorber. So here the gas goes in and then gas goes out. So here liquid comes in and liquid goes out. So for each of the stream we will define G1, GS, small y1 and capital Y1. Similarly for the outlet, G2, GS, Y2, capital Y2. For the liquid phase, we have L2, LS, X2 and capital X2. So here G1 or G is given in terms of moles per unit area of cross section per unit time. So this is the units of G here, and Y and X, these are all mole fractions. This 1 means the suffix 1 here means it's in the bottom of the curve, bottom of the absorber, and 2 means it is on the top side. Capital Y and capital X, these are all mole ratios. GS and LS, these are all molar flow rates of how do I say, this is actually insoluble gas, yeah, insoluble gas, and this would be molar flow rate of liquid, solute free liquid, solute free liquid, and this is also given in per unit area per unit time. So this is something we have done for a very general case of E phase and R phase, and already introduced these notations, and we will just go ahead and then consider some point P here, where the variables will be as follows. You will have G here at some point here, GS will be the same, and then you have Y and capital Y. Similarly, the liquid that is flowing in at this particular point would have L, LS, X and capital X. Okay. So now we may want to write a mass balance. We will write a mass balance for this particular envelope. So material balance. So this G1 Y1 is the amount of gas that is entering in this loop, and L times X is the liquid, the solute that is entering in the liquid phase from the other side. Okay, there are two streams entering this envelope, and there are two streams that are leaving. The stream that are leaving here and here, those are these two. Okay, so that's a simple solute balance, solute molar balance. Now we can write these equations in terms of mole ratios. Where we have actually now written G1 by 1 plus Y1 is equal to Gs, and that should be also equal to G by 1 plus Y. Similarly, L1 by 1 plus X1 is equal to Ls, this is also equal to L by 1 plus X. Okay. So, the conversion of mole ratio to mole fractions is something that we already discussed. So, I am directly applying those. Ultimately, you will be able to write the mass balance based on the solute free molar flow rates. Okay. So, if you think about this particular total molar flow rates G, G1, G2, these are variable, okay, because as this gas goes from the bottom to the top, the solute is getting transferred from the gas phase to liquid phase. So, therefore, the total molar flow rate will keep changing across the column, okay. But if you look at only the insoluble gas part, which is not participating in the mass transfer, that flow rate remains the same. So, that is what we define this insoluble gas flow rate Gs, so that we can put all the bases with respect to the constant molar flow rate. Okay. Similarly, for the liquid also. So, here we are assuming the liquid is not evaporating into the gas phase. So, the liquid flow rate will be constant. Okay. So, that is why we change the total molar flow rate based mass balance into a solute free molar flow rate basis. So, from here we can rearrange . So, this is an equation of a straight line. It has a slope of Ls by Gs. Okay, and this is what we call as a operating line also. And you may recollect that I showed this derivation before. So, if I were to do so I have converted this mole ratio units Y versus X, and this may be your equilibrium line. Y star is equal to function of X star. Note that I am using capital X and capital Y because I am using in mole ratio units. So, now this operating line can be a line, straight line with a slope equal to Ls by Gs, and this point here is Y2 X2, and this point here is Y1 and X1, and this is for an absorber. Now, if you have a stripping operation, you will do exactly the same. The only difference is this operating line will fall below the equilibrium line, okay, and this line will have exactly the same slope as before, Ls by Gs, this is for stripper. This for stripping operation. The only thing that is different here is what I call the top and bottom of the absorber. For the absorber, the bottom is somewhere here. It starts with the highest concentration for both liquid and gas. You can see here, if I do this as a absorption problem, the concentrations are highest for the gases and liquid at the bottom, because this is incoming gas with a high solute concentration. This is the liquid coming out after the completion of absorption. So both the gas and the liquid stream will have the highest concentration, which we show here. This is the entry point or the bottom of the absorber. And if I go to the top of it, here the mole fraction of the gas would have become lesser compared to the inlet concentration, because absorption has happened from the gas to the solute. Whereas for the liquid, which can be pure or it may have a very low amount of solute. So the top of the column here corresponds to lean concentrations, okay, meaning this point. So that's why I call this as bottom of the absorber. Sorry, I denote this as the top of the absorber and this is the bottom of the absorber. Whereas if you think about the same operation but for a stripping case, where you want to remove a solute from a liquid into a gas. In this case, since the transfer is going from liquid to gas, the stream at the top would be richer in the concentration, because the liquid is incoming with a higher concentration of the solute. The outgoing gas would have taken enough amount of solute. So the top of the column would have the highest concentrations for a stripping operation. So that's what I have denoted here as the top of the stripping column with the highest concentration of liquid and gas. And if you come to the bottom of this stripping section, and the liquid would have been spent and the gas would have been maybe clean gas or a very low concentration. So the concentration in the gas and the liquid would be the leanest. So that we can identify here as the bottom. Okay. So the operating line equation for the stripping section and absorption is the same. It is a matter of whether the line will lie above the equilibrium line or below the equilibrium line. And this is also very intuitive, because if the line happens to be on the top, you know that the driving force is for the gas to liquid. Okay. Whereas in this case, the driving force would be that the operating line will try to reach the driving force. It's trying to reach the equilibrium line from the bottom to the top. Okay. So, and then the notion of which is top, which is bottom, that denotion is also different. Those are the things that you have to keep in mind. Now the third topic that I want to talk about is the minimum. So now that I talked about the operating line having a slope of Ls by Gs, okay, minimum flow rates. So now let's say I have the equilibrium curve, kind of drawing a little differently this time. Let's say I am talking about an absorber. So in an absorber, generally the composition on the top, okay, this is a composition at the top, will be specified, okay, and that we can identify as somewhere here. So this is the top of the absorbing column. So this is Y2 and this is X2. So what it basically means is the incoming liquid will have a particular composition of the solute. Okay, this is specified because we know which liquid we are sending and we know its composition. Y2 is the target separation that we want to achieve. We want to say, I want the outlet gas to have only 1% of the solute, or it should have 99% clean. So that's a design specification. So in an absorption problem, we pretty much know or specify what is the composition at the top of the column. We also know what is the composition of the gas in the inlet. Okay, so this point is known. This point we have fixed. Now, if I choose a particular liquid flow rate and I can draw that operating line like before, this is my operating line. So once I have this operating line with a slope equal to Ls by Gs, this will tell me what would be the composition of the liquid at the bottom. So this is a liquid that is absorbing the solute from the gas and leaving the column at the bottom. So the composition x1 here determined by the slope of this line. I can do another line here. Let's say I take a line like this. This is a straight line. If I have chosen this particular liquid flow rate, then my outlet concentration would be x2, not x2, let me put x1 prime. How can I go from this red curve to green curve? What choices I have made here? What did I change? To change the slope, I have changed the, let's say, the liquid flow rate, Ls, and I change the slope smaller or bigger. The slope is now smaller. Going from the red to the green, I have decreased the slope, meaning I have decreased the liquid flow rate. So what's the consequence? If I decrease the flow rate of the liquid, what's the consequence on the outlet concentration? I'm going from x1 to x1 prime. It tells me that if I decrease the flow rate of the liquid, I can enrich the outgoing liquid with a higher concentration. So that should tempt us to decrease further and further, isn't it? Because if I take another curve with even smaller slope, meaning even smaller liquid flow rate, I can go to even higher liquid phase concentration. So the question is how much I can do this, how long I can do this. Okay, so I am decreasing this liquid flow rate and there is a limit to which I can decrease, beyond which I cannot. That limitation is based on where I am going to touch the equilibrium curve. Okay, so if I keep on doing it, at some point of time I might touch this equilibrium line, and that I call that as my minimum gas liquid. Okay, so it's supposed to be just touching above. Okay, and this would be the x1 corresponding to minimum gas, corresponding to minimum liquid flow rate. So minimum Ls is obtained by drawing the operating line such a way that it touches the equilibrium line. So this is here is an interesting question. So if I can set the flow rate to the minimum level, I can achieve the highest concentration on the liquid phase, right? And if I can operate with the minimum flow rate of liquid, cost will also be less for me because I am only using very less amount of liquid. So should I then choose this operation? Should I always choose a minimum liquid flow rate? Can we do that? Because it's a win-win situation, right? I am able to increase the outgoing liquid phase composition high at a very small flow rate of liquid. So shouldn't I choose that as the operating flow rates? Can we do that? let me give you a hint. What we are trying to do here is, we are saying that the inlet composition of the gas is specified, Y1, you cannot change that, right? And the outgoing stream composition X2, Y2 is also specified in this problem. Those are design specifications. Now you are allowed to change the liquid flow rate, and whenever you change the liquid flow rate, you are able to change the outgoing liquid composition. Now, from an economical point of view, the minimum flow rate is better for me because I am going to invest less. So obviously one would think to go with the minimum liquid flow rate, right? That's the more intuitive picture. But look at these curves and see what happens when you keep on decreasing the slope of this line going towards the minimum operating line, where it just touches the equilibrium line. What is happening to the driving force? Driving force is diminishing, right? So if the driving force is diminishing, but with a fixed inlet outlet composition, if you want to achieve this, what about the height of the column that you have to provide? If the driving force becomes smaller and smaller, then the amount of height packing that you need to provide will go up, because you are decreasing the driving force by moving closer and closer to the equilibrium line. So this is the compromise we have to make. I can reduce the liquid flow rate so that economically it is more viable, but corresponding cost will have to be increased in the providing enough amount of packing so as to reach these design compositions. So that's why we don't operate the absorber corresponding to the minimum flow rates, but this will give you the benchmark. Now I can say I will want to operate the liquid flow rate 50% of the minimum, 50% more than the minimum, or maybe 20% more than the minimum, or 100% more than the minimum. By increasing the liquid flow rate, the driving force goes up, the packing you need to achieve the same separation will go down. On the other hand, if you go to a lower and lower liquid flow rates, you can save money in terms of the liquid cost, but there will be a corresponding cost increase in providing a larger packing height for achieving the same kind of mass transfer operation. You have to think about this minimum gas flow rate is very similar to the flooding pressure drop I talked about in the previous classes, where flooding pressure drop sets the limit up to which we can operate. Okay, we want to always operate with the highest gas velocity so that we can do highest mass transfer rate, but still the column cannot flood. So we say the pressure drop corresponding to the flooding is a benchmark, and you want to say 50% less than the flooding pressure drop, 80% of the flooding pressure drop. So it kind of tells you the limit to which you can operate. Here we are talking about in choosing the liquid flow rate so as to effect the same amount of mass transfer. Okay, so when I do subsequently the mass transfer, the packing bed, the height of the absorption column calculation, you will see the significance of this, that as you keep changing the liquid flow rate, the driving force will come smaller and smaller, and correspondingly the height of the packing will go up. Okay, so this is going to be more like a benchmark for us. We are going to say calculate what is the minimum liquid flow rate for absorption. From there you have 50% more. Okay, and then what you would do is you will first find the minimum minimum liquid flow rate like this, and then you say 50% more, then you may actually come to the column, the line green, because slope is now 50% more. Okay, now this green has good amount of driving force throughout the column. If I look at the black line, you can see that the driving force diminishes when it touches somewhere here. Okay, so that's the compromise we have to make between how can I keep the driving force sufficiently big enough, at the same time how can I optimize the flow rates of the liquid. The same argument can be used for the stripping case, in which case we will talk about the minimum gas flow rate. Instead of minimum liquid flow rate, we will say minimum gas flow rate, because in stripping operation the liquid phase composition at the inlet exit will be decided. We will have a choice of making the gas flow rate. Gas flow rate is something that we can choose so as to operate to reach that particular mass transfer rate. Okay, so in absorption problem we are interested in finding the minimum liquid flow rate. In the stripping operation, we are interested in calculating the gas minimum flow rate. Okay, so now comes the example. So this problem is an example problem where we have a absorber and stripper working together. Okay, so first we do absorption, where a gas, its flow rate is given here. Yeah, so its flow rate is given in terms of meter cube per second, and temperature and pressures are also given, and then it has 2% of some vapors, and this vapor is nothing but benzene, and we want to remove 95% of this. So the incoming gas has 2% of benzene. Of this, 95% we want to remove. So this is the design specification. Y1 is mentioned, Y2 is also mentioned. Okay, and the gas flow rate is given in terms of volumetric flow rate, but you also have this temperature pressure data. So from there you can actually calculate molar flow rates also. Right, you can find the density, and we know the average molecular weight, and from here you can calculate. So the wash oil, which is the liquid phase, enters at certain temperature. It has particular mole fraction of benzene, meaning the X2 is also mentioned. Okay, the incoming composition of the liquid is also mentioned, and the molecular weight of the liquid is also mentioned. Now you can see the oil, the liquid, is circulated at 1.5 times the minimum. So that means we have to first find what is the minimum liquid flow rate or oil flow rate, and then we have to have 1.5 times of that, 50% more. And then the wash oil is ideal, and the temperature will be constant at 26. So the wash oil benzene solution is ideal, is giving an indication that you can use Raoult's law for the equilibrium data. Okay, that's not given here. Okay, and the second part of the problem is the solution, the wash oil solution coming from the absorber is heated to 120 degrees Celsius. Here we are actually playing with the solubility data now. By increasing the temperature to 120, we are now changing the equilibrium behavior of the solute in the liquid, and then this will enter the stripper at certain temperature and pressure. Now we use a stripping stream which is operating at atmospheric pressure. This is superheated to 122. The debenzolized oil that means having a particular mole fraction is to be cooled to 26 and returned to the absorber. So basically we have a system of absorber and stripper, so that the wash oil can be used in the absorber. Later on it can be removed from the benzene and recirculated to back to absorber. Okay, so if I have to plot this, you have an absorber and then you have a stripper. So here you get gas goes in, and the gas is cleaned of benzene. So here the wash oil comes here, leaves here, but enters the stripping column. Okay, maybe not like this, it will probably go like this. Okay, now you have a stripping another gas. Okay, I think it's not mentioned, it's a steam or stream? Steam, where is it mentioned? Steam, yeah, okay. So this is actually steam, not gas. So you are using steam to recover, and then steam goes out. Okay. And this is what being sent here as the wash oil here. Okay, so it basically, so it can continuously operate in this fashion. So you can see in this particular problem, what we are interested in is we have to find out what is the oil circulation rate. Okay, and this oil circulation rate is 50% more than the minimum oil flow rate. Similarly, in the case of stripping, we are using the steam 1.5 times more than the minimum. So in the stripping operation, we will find the minimum gas flow rate, and then we will increase 50% more. Okay, so the two problems are exactly the same. Okay, In one case, we will do the absorption operation, look at the line so that it touches, find the minimum, and then take 50% more. Similarly, in the stripping, you do the same thing. Okay. Let me also show you quickly. So here you can see that the data is given in terms of Raoult's law. So what I do, the Raoult's law is actually plotted here as the blue line. Okay. So this is Raoult's law, and you can see this line is not kind of a straight line but slightly curved, because this is plotted in the mole ratio units. Only in the mole fraction units it's a straight line. When you convert into mole ratio unit, it will slightly have a curved nature. This point here that you see is the Y2 and X2 for the operating line, and Y1 is mentioned 2%, right? This is Y1. Like I said before, the composition at the top is mentioned. Inlet composition for the gas is also mentioned. Now we have to find the minimum liquid flow rate. So the red line that you see here is drawn such a way that it just barely touches the blue line. This point is fixed, and this line, red line, is drawn such a way that the end point will touch the 0.02. Okay, you have several possibilities, right? Each one of them is a possibility, as long as they all stop at 0.2, and you keep decreasing until you touch the blue line. So this is corresponding to the minimum LS. Okay, and you can know what is the slope when it touches, and we know the slope is LS by GS. GS is known. Calculate LS minimum. Okay, and then you take, so the question here is only to find the circulation rate. Okay, your answer stops there. But if you are interested, you can actually go to the operating line corresponding to 1.5 times the minimum LS, and then from there you can calculate what would be the outlet composition of the liquid. Okay, same thing to the stripper. In stripping case, again you can see this line, equilibrium line, is now different compared to this line because of the operating temperature different. So when you apply Raoult's law at two different temperature, the vapor pressure depends on temperature, right? So the equilibrium line will also be different. Okay, so this corresponds to, I think, 26. Yeah, so this equilibrium line is obtained for 26 degrees Celsius. This one is obtained at 120 degrees Celsius. That's the difference. So in this case also, what will happen is this point is mentioned at the this would be the designed one, and this composition is also mentioned. Now the red line is drawn such a way that it touches the equilibrium line, and then get the minimum of LS by GS. Here LS is known, GS you will find out, and based on that this line can be drawn. Okay, and this would be the corresponding outlet gas composition. Okay. So the details of the calculation is straightforward. I will upload the calculation of this problem in Moodle, but because some of the details are missing in terms of converting the Raoult's law from mole fraction to mole ratio, and then you have to have a, you can do this in an Excel sheet. Okay, make XY data, draw the blue line for equilibrium line, and then choose this red line such a way that it touches the equilibrium line. Okay, all right, we'll stop here.